Hello, Kostis, can you please confirm if you can hear me?
Yes, Theodore, I can hear you clearly.
Perfect. Okay, hello everyone. I would like to welcome you to another Connection Wednesday webinar, our regular online meeting that gives us the opportunity to demonstrate how Idea Statica has managed to revolutionize the way that we design steel connections. I am Theodore, and together with Kostis, our support manager, we have prepared today's content, which we certainly hope that you will find very interesting. Before we start the presentation, I just wanted to mention the usual information about GoToWebinar software. So in the right side of your screen, you have the control panel. You can use this to enter any questions you might have during the webinar. Your microphones are muted by default, so anything you want to ask, just write it on the question tab. I'll just go very quickly through today's agenda, just to give you an overview. So in the first part, we are going to present a customer project, which today comes from ARUP in London, and it is a multi-column base plate. And I'm going to explain more about it in the next slides. In the second part, as always, we have a HelpDesk highlight. And today we have chosen one of the most frequent questions that we have from customers, and has to do with the comparison of the results with other component-based design software. This is something that happens very often, that customers are trying to compare the results with other software that follow the traditional component-based principles, and they find some differences. This is logical because Idea Statica is based on a finite element model that takes into account everything, for example, eccentricities, which is not the case with other component-based software. Therefore, we need to make sure that we are comparing exactly the same things and simulate properly the connection in Idea Statica. So we're going to show some examples of what you should be aware of. In the last part, so in the end, we will if we have some time, we will try to answer some questions that you might have, although we will also do that during the webinar through the question tab. So keep your questions coming and we will try to answer all of them. So let's start the presentation with this customer project, which today comes from ARUP. ARUP has been one of our first customers in the UK. Who have used Idea Statica extensively over the last 3 years in many projects, not only in the UK, but around the globe. The project is located in the city of London. It is a new office development for Generali, Italy's largest insurance company. It is located at 10 Fenchurch Avenue. It is a 420,000 square feet, 50-story building that provides commercial office space, retail use at the lower levels, and a public passageway at the street level, and also a publicly accessible roof garden. The developer was Generali Real Estate, supported by development managers Core and Greycoat, and the architectural design of the building was done by Eric Perry Architects. ARUP has provided the structural engineer, geotechnical, and security services for the development, and used Idea Statica in different parts of the structure, including these base plates on for the steel pergolas on the roof garden that we will show today. So, as I mentioned, this building incorporates a unique roof garden for the public and the tenants of the building that offers panoramic views of London within the square mile, as you can see in these pictures, all across the city to the Tower of London and even beyond that. The garden features 2 galvanized steel pergolas that you see in this slide. which is the part of the structure that we will show today, and more specifically, their base plates. Now, both pergolas are using base plates with multiple columns that essentially are these three types that you see in this slide. And our example today is actually the first one, the one that shows the three columns. So quite, although something that seems simple as a geometry, although something that cannot be easily designed with any other software. The structure has been analyzed in GSA from Oasis, and all the critical load combinations have been imported in Idea Statica for the design of the base plates. After the analysis, of course, you can have some very detailed results in Idea Statica, as you can see in this slide. So we can have the equivalent stress for the plates. We can also have the bearing stress in the concrete. And of course, Kostis is going to show some more detailed results, and also how to tackle some failures that might appear after the analysis. Before we go to that, before I switch my screen to Kostis, I would also like to thank Gordon Clanahan for the London office, who was responsible for this project and provided us with all the material, all the information about it. So Gordon, if you're watching this, thank you very much. Now I'm going to switch to Kostis to start his presentation and show you exactly how we can design this connection.
Okay, so hello everybody. Theodore, can you confirm that you can hear me and you can see my screen?
Yes, everything is perfect.
Okay, so let's move on. Today I will model the three-column variation of this base plate, and I will take the opportunity to show you our general anchoring analysis, and I will focus on solving some common problems with base plates. So let's move on to the modeling of this connection. So I will first add some hollow sections for the three columns. Let's go and add some RHSs. Let me find the right size. It's here. First, let's rename it C1. I will rotate it by 90 degrees. Have a look from the top, and again, rotate it around its axis. Let me change the view to transparent, and now I will copy this member. And again, rotate it by 30 degrees. Of course, rename it. And again, copy, rename, and again, rotate by 210 degrees. Sorry, this is minus 30. Okay, so here we have all the members. Now, one thing I would like to make clear is that in Idea Statica we have the concept of the wireframe model. So everything is modeled around our fictional node. So in order to respect this, I will move all my members equally around this node. Uh, if I switch on my local axis, I can see that I have to move all my members along their local z-axis. You can see it's this blue axis here. And to do this, I will select each one of them and move them by minus 150 mils. So all members are in place, and I will deactivate the local axis and move on with the modeling of the base plate. Now, in this demonstration, I will show you how to use our general anchoring. So instead of using a base plate operation, which is this operation here, I will go and use a normal stiffening plate. Let me change its material to 75. I will increase its thickness and then set its overall geometry. And we can see that the plate is defined, is including all cross sections. The next step is to fine-tune the shape of the outline of this base plate, and I will use the editor by right-clicking on this plate, and I will add some bevels. I will start from corner 2, then copy this one, apply it on corner number 3 here, again copy, apply on corner 4, and again copy and apply on corner number 1. Okay, this seems to be okay, so I'm accepting the changes, and my model follows these modifications. So let me see this. Let me have a look from the side. I will switch my view to solid, and the next step is to weld all these columns on this plate. For this, I will use the cut operation. So I'm welding member C1 on a plate. Let me rotate this a little bit. It becomes obvious that the weld is realized here. I will set its throat thickness to 5 mils, and then I will copy the operations and apply to the rest of the members. Now, we're going to use to make this a base plate. And the question is, how can this be achieved? So let me go back in my operations. And this time I will use a bolt grid operation. Let me add M20 bolts. But this time I will set my fastener type to be an anchor, and you can see that the plate is modified and it becomes a base plate, and we can see a foundation block at the bottom. I will set my items count to 1, and then I will start setting the geometry of the base plate. First, let's set the geometry of the foundation block. I will set its concrete grade to be 40. Let's have a look. From the top, the foundation block will have an offset of 200 mils in relation to the outline of the base plate. The depth of this block will be 400 mils, and I will use my shear force, the shear force transfer to be friction, and I will also use a mortar joint of 30 mils. The next step is to define the position of the anchors. So my anchors have 100 mils distance from the center of this plate. Let me set my rows here. And now we have 3 rows of anchors. Now let's set their anchoring length to be 300 mils and the anchoring type to be of circular washer plate of 60 mils size. It's obvious that 2 of our anchors are clashing with our columns. To fix this, I will select my grid operation and select the editor. And there, I will explode my anchors and fine-tune their positioning using this table here. So I want to move anchors 3 and 4. Let me set its X position. And then I will also try to move anchors 5 and 6. They seem to be okay. So let me apply this modification on my model. And we can see that all my anchors are in position. So basically, our model is ready to be loaded. To load this model, I will activate the loads in equilibrium. And I will copy all loading from an Excel file I have prepared. I will use the Excel import, paste, and loads are in place. Now let me calculate this. At this point, I would like to let you know that I have modified the loading and the geometry of the original configuration in order to have some failures and to make a point that you will see later on. So right now, we can see that we have failures. Now let me have a look here. So this should be 0.2 for this example. And the reason is that I want to make a point. So I'm sorry for this. Let's calculate again. Okay, so now that the solution is over, we can see that we have the software displays a summary of the results at the top left of the graphical window. So we can see here that our analysis is 100%, which means that all loads were applied. We can see the utilization of our plate in terms of plastic strain. We can see a failure in our anchors. Our welds are okay. The compression in the concrete block is okay. And last, we have a failure in shear. And this shear is, we mean the shear resistance between the base plate and the mortar. If we go with the check tab, we have we can see these results in depth. Here we have the analysis for each load case, which is applied to 100%. At the plates tab, we have all plates in idea, and these plates also include members. So we can see here items C1, C2, and C3. And if I select each one of them, at the bottom graphical window, I can see an unfolded view of my member. We can see the material, the thickness of the member, the critical load case, the extreme von Mises stress, and the extreme principal plastic strain. Here we have our anchors tab, where again you can see the results in detail. Since we have failures here, I will come back later on. I will move on to the welds, where again we have a table of results. For here we have welds per member. So if I select a table row, I can see at the bottom view, I can see that the member which is welded on the base plate is highlighted with an orange outline. Next to this view, I can see an unfolded diagram of weld stresses, and of course we can see the maximum, the resistance, the maximum applied stress. We can see the maximum plastic strain and the stress components that are required from the code for the calculation. Next, we have the concrete block, where I can see the concrete compressive strength, and also we can see the hatched area, which is the effective area that is required from the code for this calculation. I forgot to show you that if I extend these rows, I can see the code formulas that display the code calculation. And last, we have the shear. So let's start from this. Here we have a failure, and if I extend the row, I can see the code formulas and the calculation for this simple check. Now let me go in a presentation I have prepared, and let's have a look at the code to see where how the resistance of how the design friction resistance is calculated. We can clearly see that it's a function of two factors. The first factor is the coefficient of friction between the base plate and the grout layer, and the second factor is the design value of the compressive force. In our case, the design value is given. We cannot change this unless we can influence the global design. But what we can change is the friction factor, which for sand cement is 0.20 according to the code, but for other types of grouting, this coefficient of friction can change. So in our case, let's say that we use a different grouting, which for example provides a friction coefficient of 0.3. We can replace this here and then calculate again. At this point, I would like to draw your attention to the fact that there are two friction coefficients. So you have to be very careful. We have one friction coefficient for the concrete block and one friction coefficient for slip resistance. So you have to be careful and replace the value in the friction coefficient of concrete. So let me press OK and calculate again. And we can see that the shear utilization drops to 77.4%. Excuse me. So let's move to the anchors and see how can we heal this. Here we can see the tension force in its on it for each anchor. Let me rotate this a little bit, switch at strain check, and activate the bolt forces. I will sort the results by the utilizations by pressing at the column header here. We can see the results are now sorted, and I can see if I click at the last row that the critical value for the checks are for anchor A9. Anchor A9 is now blacked at the bottom view, and of course I can spot it in the 3D window because I can see its name and the value of the tensile force here. Now the critical check is for the concrete cone breakout resistance. Now if I extend this row, I can see all checks, formulas for all checks, and here we have the concrete cone breakout resistance of an anchor. I can also activate the concrete check, and at the bottom window I can see my base plate, I can see my blacked anchor, I can see the outline of the foundation pad, and I can see with a red dashed line. Now let me change this to the critical load case for the anchor. And we can see the red dashed line, which is okay, I skipped a part. So the first thing it comes next. So I'm sorry for this. The first thing we have to check in this calculation are the installation factors. The default value in Idea Statica for the installation factor is 1.2, but in the code we have some choice here. So we have this factor can be from 1 to 1.4. So in our case, we can have a high installation safety And again, before proceeding with the concrete code checkup, I can come to my code setup and set the high installation safety to 1. Let's press OK and calculate again. And we will see here that with the reduction of this factor, we have a further reduction of the utilization of the anchoring. So we need to take care and see what options we have from the code. So again, I will sort my utilizations using the table header. Again, I will extend the calculation for A9. I will activate the concrete check. And let's move to the next slide, which will display the meaning of this red dashed area. And this dashed area is the combined area of concrete cones for a group of anchors. And as you can see, this is directly related to the characteristic resistance for the concrete cone breakout. So if you have a really low resistance in concrete cone breakout and you need to increase it, this factor can influence the results. Okay, so let's see how this area is produced. And we can see that it is produced by the superposition of individual concrete cone anchors. So for each anchor, we're adding all their concrete cones. And all these cones are limited not only by the anchor distances, but also by the concrete element edge distances. And in this particular case, since we can't move the anchors apart, the limitation is the distance from the concrete member edge. To make this clearer, let's have a look at the concrete cone of an individual anchor, where in this particular case, we have an effective height of 300 mils. For this case, we can have a concrete cone that extends up to 1.5 times 300 mils, which equals to 450 mils from the anchor center. Now, if we have a look to our structure, we can see that we have adequate distance between the column bases. This means that we can increase the concrete offset and include the full concrete cones. So let's go back in Idea Statica once again. Let's switch the view to solid, select. I have to go to the design tab, select my foundation pad and extend my foundation by 400 mils. And I will allow the full development of the concrete cones. Again, let's calculate. And now you can see that all anchors are passing the checks. Last, there are cases that nothing else works. So when nothing else works, the latest valid the latest valid code 1992.4.2 adds support for the design of complementary reinforcement with a simple strut and tie model. Now let's say that nothing else works and you use this additional reinforcement. In this case, the supplementary reinforcement resists failure. So you don't need to check for your concrete breakout resistance. In this case, you can deactivate the check from our code setup. So let me go back. And in this case, you can deactivate this from here. Since we don't have too much time, I will stop it here and pass the presenter to Theodore to move on.
Okay. Thank you, Kostis. So just quickly, before we move into the second part, so as I mentioned earlier, this is one of the most common, frequent questions that we have from customers when it has to do with the comparison with other component-based design software. So today we're going to show you this example that you see on the slide. Of course, there are many different cases that you have to probably compare. Of course, we cannot cover all of them, but through this example, you will see what are the principles, let's say, and what are the things that you need to worry about when you're trying to compare results. Another thing that I would like to mention is that if I switch to my view, if I switch to my browser, I just wanted to show you. So it's, let me just switch here. Okay, so if you go to our resource center, so this is the home page of the resource center. So everything that we have concerning the software is included in this web page. So if you go to connection and verification and articles, we have many different types of connections. We have many different verification examples that includes not only the Eurocode, but also other codes. So if I go, for example, in this end plate minor axis connection, you can see that we have a detailed description about the comparison, charts, etc. So very detailed information about how the CBFEM method compares with the standard component-based through specific examples. So feel free to go through this resource center. We have a lot of information. Of course, we also have the theoretical background of the software, really important to read, to understand exactly how the software works. So with this, I'm going to switch back to Kostis to show you the example that we have prepared for today.
Okay, so this was the connection that came to our help desk, and the client was asking why it passes all checks. Let me solve this. And you can see that our connection passes all checks. Our client tried to solve the same connection with another software based on the component method. And here are our findings. First, when we compare connections, we must make sure that the geometry must be identical. Now, in this case, the client uses a different gap for our fin plate. He used a different distance of the bolts from the welded end of the fin plate, and last, he used different distances from the top. So let's go back in our model and modify this a little bit. Let's go modify this. Now, another thing that was hard for our client was that the definition of bolts in our stock fin plate operation, bolts are defined in relation to the center of the overlap. I'm sorry. So in this case, we have to move this bolt column closer to the edge of the beam, because actually this distance was really critical. In order to do this, I right-click on the fin plate and use the editor. Here I will explode my bolt, and I will play around with my X and Y coordinates. So I will move my bolts by, by minus 15 mils. And I will also move them in the Y direction. So now they're eccentric. The next thing was that if I click on my member B1, I can see here that the client set the model type to this one. So he's not allowing moment. This is wrong. So I will switch this back to allow the full moment, the full stress vector to be applied. And next, when we're comparing connections, we also have to make sure that loading is identical. So in this case, our client defined a shear force of 60 kilonewtons, but in idea Statica, probably because it is a remnant of experimentation, he also had an additional force of 17.9 kilonewtons. This is an axial force that, when it is applied to the member, due to the eccentricity with the center of the bolting, it produces an additional moment. So in order to have comparable results, we need to eliminate this axial force. Now let's go back. Let's go at the load case and eliminate this force and calculate again. And now we can see that we clearly have a failure here. Our bolt is failing. Now let's go back to the presentation and compare the results. So here we can see that we have a bolt failure, which is comparable to the bolt failure in the component method software. And we also have high weld utilization in line with the component method calculation. So like Theodore said, we have a rich library of verifications that are available online. And we also have published from Professor Wald the benchmark cases for advanced design of structural steel Connections, which is available from our website, and it is in its second edition already. With this, I conclude my presentation, and I will return the presenter back to Theodore.
Okay, thank you very much, Kostis. So I think we have answered pretty much all the questions that we have through the question tab. So if there is anything else that you would like to ask, just write it on the question tab. Let me see if we have something. There is a question, Kostis, is it possible to model fitted bolts?
I'm not aware of fitted bolts. What does it mean?
Yeah, can you, with a close tolerance?
Yes, in what sense close tolerance? Bolt hole tolerance?
Yeah, bolt hole equals bolt diameter to avoid slip instead of using preloaded bolts.
Well, I'm not sure. I have to discuss this with our developers. Our bolt models take into account the natural account for this tolerance, but I'm not sure if we can set this to a value of 0 or something. I have to ask.
Okay. Another question that we have. Can we use perpendicular anchors to already existing ones?
Well, yes, actually, you can do this out of the box. And well, we see this question a lot in our help desk. People must be aware that when anchors are used in this way and they're perpendicular, there is an interaction between them. The problem is that right now there is no research, there is no guidance in any code, so we can't do this. We can't do this in a way that it's code compliant.
Okay. There is another question. Will it be possible in the future to check the plate which will be poured in the foundation block?
Casting plates.
I think this is what means. It means casting plates, probably. So yeah, yes. Casting plates is something that we consider. We do not support at the moment, but this is something that we consider for future development. If this is what you mean, yeah. Well, there's a lot of questions coming. Can I use Idea StatiCa for checking base plates for telecommunication columns? Would the software allow to check resin anchors too? Yeah, I don't see why it cannot be used for telecommunication columns. If there is a specific thing that you could like to have, just let us know. Resin anchors, I think we do not support at the moment. Can the anchor plate thickness be defined in the software? Yes, of course. The anchor plate.
The washer plate.
The washer plate. Yeah, yeah.
Well, actually, at the moment, it is not defined, and the reason is that it is not accounted in the calculation because there is no such calculation in the code. So the washer plate thickness is up to the designer using good practice.
In future releases, will we be able to design partial penetration butt welds? Yeah, this is something that we have as a request for a long time. This is, of course, something we consider to have in the future. But then it has to do also with the code. So I'm not sure if it is completely supported. Yeah, this is another similar question. Are there available other types of welds available than the fillet welds, like full of partial penetration welds? Yeah, we have, of course, you can define different types of welds. You have double fillet, you have full penetration. Partial penetration is not something we have at the moment, as I mentioned earlier. Check of connection anchors in case of fire. Is this something which you will consider in the future? I'm not sure exactly what check is that.
Yes, it's for fire resistance. Yes, I'm not sure for the differences, but I'm noting this. Fire resistance. Okay.
Let me see if we have something else. Can we combine friction and shear of anchor bolts to obtain overall resistance of the base connection?
Yes, for the moment, no, but I think that our developers are aware of this and are working to allow such calculations.
Okay. I think this is probably all the questions that we have, and since I think it's already 15 minutes after we started, I think we can conclude here the webinar. There is a question about the recording. Yeah, this is something I will mention later on. So if you have any more questions, feel free to send them to us through email, and we will answer them during the day. So I will just go back to my slide. So after the webinar, you will receive a short survey. Please fill this survey. It will help us to become better in delivering these webinars and see exactly what we need to improve, what we would like to have. The recording will be available till tomorrow in our website and on YouTube channel, so you will be notified for that as well. And of course, if any of you haven't used the software, I strongly suggest to download the trial version from our website so that you can see for yourself all these advantages that Idea Statica provides. And of course, as I mentioned earlier, you can go to the resource center and check all the material that we have, the theoretical backgrounds, verification examples, tutorials, everything is there. The next webinars that we have planned is for next Wednesday. So we have a webinar that will demonstrate how we can design a column with bracket according to ACI, and this is with Idea Statica Detail. So really interesting webinar about this unique technology that we have developed for the design of concrete discontinuity regions. And the next Connection Wednesday will be on the 20th of March, and this is where we will show you our cloud solutions. So you can immediately register through our website for these 2 webinars. So let's conclude this webinar for today. So I would like to thank all of you for participating and sending all the questions, and we are looking forward to see you in one of our next webinars. So goodbye.
Bye.